Okay. All right, let's talk physics a little bit. Here we go. Okay, so we're going to start talking, we want to start exploring physics a little bit. I guess anything we need to hit from that, we talked about precision and accuracy, we talked about how to do computations or calculations involving measurements, right? You guys got some assignments to work on and practice that. Let's take a second and talk about units, very briefly. I'm not going to spend a lot of time on this. So in physics, we use standard SI units, right? Which SI units sometimes are called MKS units. You know what that means? What's that mean? I'm going to read it. Haven't done reading yet? Okay, do the reading. MKS units. So that means we're building units from the fundamental quantities, meters, kilograms, and seconds. And then later on when we get into, we'll add amps to that too when we get into electricity and magnetism stuff. But that's a long ways away. So for now, everything is built from the base units, meters, kilograms, and seconds. Okay. So for example, when we come to talk about force, we're going to build a derived unit for force, which we're going to call the Newton, but it's going to be built from meters, kilograms, and seconds. Right? Okay, make sense? So we've got, and sometime when you guys are working on assignments, we'll take a little time and we'll maybe talk about what are the standards, what have the standards evolved to be in science for the meter, how do we specify a meter, how do we specify a kilogram, how do we specify a second, because they've evolved a little bit, they've gotten more accurate, but we'll hit that later. So what I want to talk about today, in order to talk about physics, in order to talk about mechanics, we're going to talk about how physical systems evolve, how they change. And particularly we want to look at things that involve, like we're going to kind of veer towards talking about, for example, forces and the impact that forces have on the world. And along with that we'll talk about energy, for example. But to get there, would you agree that we need to be able to describe motion? Okay. That makes sense? If you think about the universe is really interesting insofar as it changes, right? It changes from time to time, and in fact, time is that we could spend a lot of time just talking about time. I mean, what does time really measure? What is time?
A series of moments.
A series of moments. Okay, that's not a bad way of saying it. What distinguishes one moment from the next?
Repetition.
Yeah, I mean, that's interesting. It's almost a philosophical point. What distinguishes one moment from the next? Say it again. Yes, time is much more malleable than you might think. We depending on where we are and what we're doing in the universe, our time would pass at different rates, and we'll talk more about that later. But let's just talk about, just for a second, what is time? I mean, that's not a bad way to start. It's a series of moments, kind of. But in order to, really pin that down, what about the series of moments? How do you define a moment? Isn't that kind of almost a circular definition in a way? Because how do you find moment A, how is moment A different from moment B? Potentially. Before it. Okay, that implies some kind of temporal relationship though, right? Temporal meaning time related, right? So time has to pass between those moments maybe, right? Okay, but what is that? In order for time to progress, and we've got interesting ways of defining this in physics. Probably the best way to define time in physics is by, probably would be related to the flow of entropy. Okay? But that's a topic for later. Okay? But we can kind of distill that down to something easy. Would you agree that time really only makes sense in the context of change? If nothing changes, has time elapsed? No. Right? If nothing changes, then that's not time. Then no time has passed. Something always changes. What's changing if we sit perfectly still in this room? What's changing? Okay, yeah, our hearts are beating, it's right. What if we want to get past that, and we're going to download our consciousness into robots, and we're going to sit here and we're able to switch ourselves off and switch ourselves on to save energy, right? So as we sit here and stare at the clock, what's changing now?
Carbon-14 is slowly decaying.
Okay, carbon-14 slowly decaying, sure. Okay, let's say we've, say it again? Yeah, the clock, for one thing, the clock, right? Even if everything else were still, the timepiece, whatever is keeping the time has to be changing. That's what a clock does, it changes. Changes from state to state, and that constitutes the passing of time, right? Does that make sense? So time is change in a sense for physics, right? Okay, so we've defined time loosely. We'll get back to that. What about this statement then? So we're going to describe some motion. I'm going to travel, how precise is this? I'm going to travel 6 meters. Did that give you an accurate picture of what I'm going to do? Not at all. What would I need to add to that to make it more precise?
The direction.
Okay, the direction. Okay, I'm traveling 6 meters north. I need a starting point too, don't I? Right? I need a starting point. And an ending point maybe, right? Okay. What else might I add to that to make it even more precise? Didn't say how long it took. Yeah, so maybe I need a starting time and an ending time. Now we're starting, let's say I say this then, I start at 12 noon precisely. I am going to move 6 meters north over a period of 3 seconds. That's getting more precise, isn't it? Right? And I'm going to be starting from the center of the door to my classroom. Now we're starting to pin things down a little bit, right? But you see in physics, we have to be able to specify very precisely the parts of the motion that we're studying, right? So we'll get back to time, but then something pretty basic is position, right? We have to be able to pinpoint a position. Okay, so how might we do that? Well, if we're going to talk about our universe has 3 extended dimensions, and so I might say, for example, that dot right there is the reference point to our position, right? And from that reference point, I could identify maybe an x-axis, horizontal axis. I could define a y-axis. How many dimensions is that? 2. So that would allow me to specify the position of that point in this plane, right? But if I want to talk about our space, because we live in a 3-dimensional universe, right? We have a volume to our space, then I would also have to have another axis coming out of the board, maybe called the z-axis, right? And by specifying just those 3 numbers, I could specify the position, of any point in space that I want to, any place in the universe, right? So if I said, for example, from here, I'm going to maybe define some kind of an ordered triple. And we're not going to deal with things in 3 dimensions. We're going to start off with 1 dimension. But I just want to give you kind of an insight into where we might go with this. If, let's say, this ordered triple represented the x and y and z coordinates in meters, what would this mean? That gives me a position, doesn't it? Where? Starting here, what do I do? Go in this direction, 1 meter. Good. We'll talk more about that. So I go over 1 meter. I'm going to go up in the y direction 1/2 meter, and then right there. Right? That's a point. Okay? Does that make sense? Okay? Okay, so let's make this simpler. What we're going to do here is we're going to talk about motion, and kinematics is really the topic that we're starting to delve into here. What do you suppose this means, by the way? What does kina mean? Motion, right? And matics would be like the study of, right? Okay. So we're studying, this is the study or the description of motion, right? we're going to distill this down to just one-dimensional motion at first, and then it's really surprisingly simple to generalize one-dimensional kinematics to two-dimensional kinematics and eventually to three-dimensional kinematics, right? It's a little more complicated, but not horribly more complicated. So let's define this a little differently. Let's say that the starting point now is going to be this vertical line right there, and I'm just going to move along the front of the room. That's it. Okay? So if I wanted to find my position relative to this point, what would my position be? Let's say I'm going in meter increments to make things simple. Where am I right now? What's my position? What do you think?
2 meters.
If that's the starting point right here, where am I? 1 meter, right? And is it positive or negative? Positive, right? Because our convention is going to be that just like on the x and y axes, to the right is going to be the positive x direction. And we're just talking about motion along the x-axis for now. And up is the positive y direction. Down will be negative, right? Why is it that way? It's because we've made it that way. We have to all agree, right? So that's our convention. All right, so I'm at a distance, or I'm at a position of positive 1 meters. Where am I right now? About negative 2 meters. Would you agree? Okay, pretty simple. So my position could be positive or negative depending on where I am, right? Okay. Have you guys talked about scalars and vectors in your science classes?
Yeah. Science.
Or math classes?
I've talked about vectors in my math.
In your math classes? Okay. So what's the definition of a scalar quantity? Does anybody know? Scalar quantity is a quantity that can be measured by one thing, and that's a number. So give me an example of a scalar quantity. Most things are.
Height.
Height. How tall are you? What page are you on in a book? One number. What's the temperature in the room, right? A number is sufficient. Most things are that way, aren't they? In fact, how fast you drive. Look at your speedometer in your car. Right? Gives you a number back. That's a scalar. Okay, what's a vector? So I'll make a note of this and then. One thing, and that's called a magnitude or a number. Okay? Let's compare that to a vector. Vector's got two things, right? Vector's got two parts to it. One is a magnitude, just like a scalar. What's the other thing? You think? Direction. So let me ask you this then. If we go back to our previous example, here's our reference point. If we say that this is a position of positive 1 and this is a position of negative 1, do you suppose that position is a vector or a scalar quantity? Vector. It's a vector quantity, isn't it? Right? Because the magnitude stayed the same in a sense, right? The magnitude means absolute value, right? The magnitude of the number in both cases was 1, okay? But the direction was indicated by the sign, okay? We could just as easily have said, if we don't want to use a sign, that's south-ish, right? That's north. We could have also said 1 meter south and 1 meter north, right? The magnitude stayed the same, but the direction changed. Okay, that's position. What about distance? How far am I from the reference point? Let's say I'm just going to be 1 meter. Okay, 1 meter. How far am I now? Do you suppose distance is a scalar or a vector quantity? It's a scalar quantity, right? If I say, how far did you go on a run? You're going to tell me a distance, aren't you? Yeah, I ran 6.5 miles. Does that imply anything about where you went or what direction you went? No, it's just a, right, it's just a distance, so that's a scalar quantity. So they're different, aren't they? Position is subtly different in an important way than just distance, okay? So position, okay, we got it, pretty simple. Position's pretty boring, right? Position really only makes sense if you're talking about something at a specific moment or if something is frozen. But in physics, we like to study change. So what would you suppose we'd call this? If I start at a position of -2 and I end up at a position of +1, I've changed my position, right? Any idea what we'd call that? So we started, I'm going to write it this way. So we started with position, and our position is on the x-axis here. So I'm going to say that my initial position, and I put a subscript of 0 there. Okay, and that implies that at the time 0, when we start the stopwatch. And we're always going to pretend that we're starting a stopwatch when we tell these stories, right? So my initial position was -2 meters, and my final position was +1 meter. How far did I travel? 3 meters, right? So something must be, to get to 3 meters, didn't I just do 1 meter minus -2? Right? So I did something like my final position minus my initial position. That's an important quantity. Okay? We call that, in physics, displacement. Okay? And how do we denote that these are, here's another issue. How do we denote that these are positions instead of distances? Like, how do we know that this is a position of 1 meter and not just a distance of 1 meter? We put a little hat on. It's called the vector hat. So we put that hat, it implies that it's a vector quantity. I think in our textbook, they just make it, I can't remember if they use vectors or not. In the online, I'm not familiar enough with the online text, I can't remember. I hope they use a vector symbol, but if they don't, a lot of times textbooks will just make a vector bold and a scalar not bold type, okay? So this is displacement, all right? Now what if we change this around? What if I start at +1 meters and I end up at -2 meters? What's my displacement then? It's -3, isn't it? Why is it -3? Because my final position is -2 minus my initial position, +1. What's -2 minus 1? -3. But it makes sense in the context, right? My direction, I moved in the negative direction. Displacement is a movement, isn't it? Right? But it has a direction associated with it. Okay, how far did I walk in both cases? 3 meters, right? Okay, so the distance I traveled is different than the displacement, isn't it? Right? Okay, distance can also mean, this gets confusing, and you have to really articulate what you're talking about in physics. So let's say I do this. Let's say that how do I do this? Sure. Back to this guy. Okay. So let's write down some examples here. I guess let's put some. So magnitude, what are some examples of magnitude then, did we say? Of scalar. We said height, weight, all that stuff. How about kinematic quantities? Let's limit ourselves to just what we're talking about up here. What's an example of a kinematic scalar? Distance. Okay, so that's going to be something like distance. Okay, what about a vector? What's our vector scalar quantity? Displacement. There's one. What's another one we talked about? Displacement is displacement because it's a change in what? In position, right? There you go. So position. Okay, makes sense? What about distance? Even just talking about distance is misleading. Okay, here's another example. Let's say that that I'm going to start here at +1 meter. I'm going to make this trip. I'm going to go out here to -2, and then I'm going to come back over here to +1 again. Okay, what's my distance? Well, okay, it could be 6, right? Because maybe distance implies distance traveled, right? It could be, I could say it's 1 meter at the end, right? My final distance is 1 meter, right? Probably distance is implying distance traveled in this case, right? So distance traveled is how far did I walk? Well, I walked 6 meters. Okay, what's my displacement for the trip? 0. Make sense? Because I went in this direction and I came back, and so my net displacement, for the trip, my displacement is my change in position. Well, my final position is the same as my initial position, so it's 0, right? Okay, so we got kind of a grasp of that. Let's go one step further forward with it then. Let's talk about the definition of velocity and speed. Okay, now we're going to add another wrinkle to this. Okay, displacement and position are pretty boring, but now we'll add speed into the mix. What is speed?
Speed. Changing distance over time.
Okay, speed is distance traveled over time maybe, right? Okay, does that make sense? You've always heard the expression distance over time. Okay. So if I get in a car and I travel 100 miles in 2 hours, what's my average speed? 50 miles per hour. Okay, does it matter that I went to, where did I go? I went to Tri-Cities and back? No, I still traveled 100 miles, 100 miles in 2 hours, so I still had an average speed of 50 miles per hour, right? Okay, what's my, so we could write that as, well, no, I'm going to leave it like that. Okay, how about, my displacement? Okay, what if I travel 100 miles to Tri-Cities and back in 2 hours? What's my displacement? 0. Okay, so what do you suppose velocity is?
Displacement over time.
Okay. Velocity is kind of like the vector analog of speed, right? Just like distance is to displacement, like speed is to velocity, or distance is to position, like velocity or speed is to velocity. This is a vector quantity. So this is going to be displacement, change in position over change in time. Okay, that's average velocity. Okay, I should be more specific about that. For now, we're talking average velocities. Okay, so if I go, if my position, change in position, or my displacement is 0, then my average velocity is actually 0. As the Earth travels around the sun, we could calculate its average speed, how, over the course of 1 year. How could we do that calculation? If here's the sun, and here's the Earth. Why is it doing this? Here's the Earth traveling. Oh, I lost my sun. Here's the Earth traveling around the sun, right? Here's the Earth. And I want to know what its average speed is going around the sun. What are some things I maybe would have to look up in a book? Yeah, really. If I just knew the mean distance between the Earth and the sun, how could I figure out average speed? What could I do?
Calculate the circumference.
Okay, yeah, I know circumference is 2 pi r, right? If I know the radius of the Earth from the sun, about 93 million miles, right? Then I could do a rough calculation. We call this a shirt sleeve calculation in physics. I could just scratch something out. I'd know the radius is 93 million miles, right? Times, 2 pi times that, divided by what? If I want to find, let's say we want to find it in miles per hour. Okay, I'm going to calculate the circumference in miles. How am I going to find the time?
365 times 60.
Oh, 365 times 24. Yeah, and it's really 365 and a quarter. So we could do that. So let's figure it out. How fast does the sun move, or is Earth moving? That's kind of interesting. It's always fun to know this stuff. Okay, whoops.
I need to find my calculator.
Okay, so we got, there we go. So we said 93 million miles is about the distance, right? So that's 93, 1, 2, 3, 1, 2, 3, times 2 pi, right? 2 pi r. So times 2 times pi. So that's the circumference, big number, okay? Divided by the quantity, 365.25 times 24 gives us pretty fast, right? So it's going about, roughly, relative to the center of the sun at least, it's going about 66,659 miles per hour. Pretty fast, right? Okay, that's good to know. That's the average speed of the sun. Okay, what's its average velocity as it goes around the sun, the Earth?
0.
Yeah. Over the course of 1 year, it's 0, isn't it? Right? Because it ends up right where it started, relative to the center of the sun. That's right. Okay. Let's try something a little different here then. So how about if we... Yes, sir.
So, if you wanted to find the velocity of less than a year, so it wasn't 0,
Yeah.
could you express that in either like the long way around or like the short way?
Okay, good question. So what if we want to calculate the average velocity over half a year? That's different, right? If we calculate the average velocity over half a year, that means we're going to start, let's say we're going to start here, and we're going to end right here. And so this is the path we're going to take, right? Go around the sun. Okay, how could I calculate the average velocity then? It's a vector, isn't it? So I have to have both a magnitude and a direction. Is the average speed going to change based on our last calculation, by the way? No, it'll be the same, isn't it? Right? Would you agree the Earth travels at about the same speed around the sun the whole time? So it makes sense that the average speed, it should cover about the same distance in any increment of time, right? Okay, so yeah, that one should stay the same. This is going to change a lot, though. How would we do the calculation? What's the direction of our average velocity going to be based on this picture? We're starting here and ending there. No, negative. Okay, yeah, it could be, yeah, but be descriptive, because I mean, what is the arrow going to point from and to? So if I want to, we could do it right now. We could walk outside and say, we could all point and say, okay, we want to define the average velocity vector for the next half a year. Where would you all point? Imagine we're outside, and I'm telling you, just point. Tell me, where is it? Average velocity vector for the next half a year.
Right towards the sun.
Yeah, right towards the sun, isn't it? Does that make sense? If I start here and I end up over there, well, where is there relative to here? Halfway around. Isn't the sun going to be in the center of this circular orbit? Right? And I'm going to be at the exact opposite point in the circle, right? It's an ellipse, but we'll call it a circle, pretty close to a circle. And so to get from there to there, here's the vector, isn't it? That's my starting position. That's my ending position. If I had drawn that correctly, it would have gone right through the center of the sun. Make sense? Okay? Right? That's an average velocity over an interval of time. Okay, so then we know what the time's going to be. It's going to be half a year, so that's just going to be 0.5 times whatever we calculated before. 365.25 days times 24 hours times 0.5 tells us the time. What's the distance going to be? Roughly.
2 times 93 million?
What is it?
2 times 93 million?
Yeah. Right? Make sense? It doesn't matter how far we traveled in this case, does it? What the distance we traveled was. The change in position is going to be the difference between that spot and that spot, and the line connecting those is 93 million and 93 million more, right? Make sense? So 186 million miles divided by half a year in hours is going to give me my average velocity there, isn't it? Right? Make sense? Okay? So you got to be careful with this with this average velocity thing. Velocity is different, right? Velocity is a vector quantity. How could you be driving in a car and have constant velocity? How would that be? Raise your hand. So, let's try. Be bold. What do you think?
Wouldn't we have to go in a straight line?
Yeah. If I'm traveling in a straight line, I could be driving in a car and driving at constant velocity, right? Let's say I have my cruise control on. How could I have my cruise control on so I'm traveling at constant speed and not have a constant velocity? Go if I went up and down hill, sure. Okay, what's another example?
Turning.
If I turn. I go around a corner, right? I go around a corner. If I go around in a big circle, for example, with my cruise control on, my average velocity for one circuit around the track is 0, right? Okay, does that make sense? Okay, all right. Okay, so now here's the challenge. We've talked about average velocity, right? Average velocity is useful, or let's even just say average speed for a second. That's what we would use more often. Average speed would be useful if you were planning a trip. Okay, let's say you're planning a trip and you estimate that with all your pit stops, what would be a reasonable average speed for a long road trip? Like how many miles per hour? So, okay, but then you're going to stop and get food, and you're going to have to, go to the bathroom. And
60.
60 maybe, over the course of, if we're doing a long road trip. That might be a useful number to have. Why? Okay, well, know what time we're going to get there. If we're traveling to Bozeman, Montana, we want to know roughly, if that's the rate at which we're average speed on a road trip, we get a pretty good estimate of what time we're going to get there, right? Does that make sense? So average speed is useful in that sense. In other senses, maybe it's not so useful. If, let's just say that we're cruising down the road and we're going from here to Portland, and we go zooming by a cop at about twice the speed limit, what's probably going to happen?
I don't think so, going 140 miles an hour.
Well,
I don't know, cops go pretty fast on the highway.
yeah, so we're going to get pulled over, right? Is it going to matter if we tell the cop, well, hey, listen, I was planning on stopping in Multnomah Falls and taking a break for a while, so my average speed was only going to be 7. It should be fine, right? It's not going to work, right? Okay, so what is the police officer more interested in than my average speed, probably? My what? Current speed, or what we might in physics call our instantaneous speed, right? Okay, so if we measure average speed by looking at distance over time, and by extension we'd measure average velocity by displacement over time, we ought to be able to maybe work towards a way that we could calculate an instantaneous speed or instantaneous velocity, right? How could we do that? Any ideas? Let's take a trip to Hermiston. If we take a trip to Hermiston and it takes us exactly half an hour to get to Hermiston and it's 30 miles away, that's an average speed of what? 60 miles an hour. Let's say we're going in a straight line the whole way, so we'll be making an average velocity of 60 miles per hour, due west, okay? Does that mean we're going 60 the whole time? No. Okay, as we go by Rue Elevator on the way, that does not mean that we're necessarily going 60, does it? Right? How could we get a more precise estimate of how fast we're going by Rue Elevator?
Small distance measurement.
What, say it again?
Smaller increments of measurement.
Smaller increments of measurement. So what if we took like a mile surrounding Rue Elevator, and it turns out that in 1 minute we're traveling a mile? What's that telling us? What's our average speed there? Okay, and that's a more reliable measure, isn't it, of 30 miles divided by half an hour. If we want to get even better, well, we'll make it shorter. Make it a 100-meter stretch. Want to do better than that, make it 10 meters. Want to do better than that, make it a meter, right? A car's not going to change its speed much over a meter, is it, right? And so, now we're getting at something a little closer to an instantaneous speed or instantaneous velocity. So calculus, folks. If we want to get an exact, and this is, if you're on calculus, don't fret, it's no big deal. I mean, this is not like we're going to be tested over this or anything, but this is a good connection to calculus. What could we do in calculus to define an absolutely precise instantaneous speed or velocity?
Is it a derivative or an integral?
Neither. What would I do to the time, or to the, let's just let's say the time duration maybe of the interval that we're measuring? How much? How much can we?
As much as you want.
Okay, but I'm always probably impeded by technology a little bit, right? But theoretically, what does the calculus tell us? What's the word we use when we want to approach a value that, we could maybe take a limit, couldn't we? We could maybe take a limit of how far of the distance we're traveling with respect to time as the time interval or the distance interval approaches what? So we went from 30-mile interval to a mile to 100 meters to 10 meters down to 1 meter, right? Let's go ahead and just use distance intervals. That's fine. We can do that. So what are we going to let that distance interval approach if we want to get an absolutely exact instantaneous speed reading? Zero. Yeah, we'll take a limit as the change in distance or the displacement approaches 0, for example. Probably in reality we do it as the time interval approaches. But either way would work. We can make either way work, right? Does that make sense? So if we want to really talk about instantaneous quantities, we have to use calculus. And I don't know, have you taken a whole calculus class?
I haven't taken Calc 3 yet, but I've
Okay.
taken Calc 22.
So unless you've taken, and nobody in here except, we got one person that's taken maybe calculus. So no, we haven't gone far enough in calculus with virtually anybody to really explore, but we get the idea. It doesn't really hamper us much, does it? A speedometer tells us instantaneous speed, right? Does that make sense? Okay. All right. I think, when are we out of here? 2 minutes. 2 minutes. Okay, I'm going to throw, there's an assignment that I'll put, here's the assignment, by the way, if you want to, I'll put it on the website. So this is the assignment. There's just a few kind of conceptual questions, just jot them down in a notebook, no big deal. So 2.1 talks about, these are just 3 short sections in the book on kinematics, kind of introduction to kinematics. This is about distance and displacement. 2.2 is about vectors and scalars. And then 2.3 is about speed and velocity. And you got to do the reading, because the reading is going to go into a little more depth than we did. And we'll talk more about these as we work through this stuff. But here's the thing I want to ask you about right now. And this is a many week conversation that we'll periodically take time to discuss. Okay, for all this stuff to make sense, it implies that when we talk about position and velocity and all this stuff, that we're measuring differences in events, right? Moments in space and time. It implies that it makes sense that we can measure those against something. That there is some arena in which all this stuff makes sense. Call it space. Okay? Is there such a thing as an absolute space? That's what I want to know. Is there such a thing as an absolute space against which we can measure all this stuff and it makes sense? So we'll talk more about that later, but start to think about that.
Theoretical physics.